Welcome to another module in this massive open online course on estimation for wireless communication. So we are looking at, in the previous module, we have started looking at the approximation error of an equalizer, correct? So we have formulated the system model of the equalizer, derived the least squares equalizer, that is C bar, the equalizer vector C bar from the employing the principle of least squares, and for that particular equalizer we have started computing the approximation error, alright. So first we have formulated our system model as y bar k equals h, x bar k plus v bar k, right. This is our ISI system model for inter-symbol interference, where ISI stands for inter-symbol inter-symbol interference, and we have demonstrated the R-tap equalizer for this is given as, we wanted to construct an R-tap equalizer for this, and the R-tap equalizer C bar for this is given as C bar equals H transpose inverse H times this vector 1 bar 2, where this vector 1 bar 2 is basically equal to the column vector with zeros everywhere except in the second position, counting from 0. Okay. So this is the expression for the equalizer vector C bar derived employing the least squares principle, and then the equalizer itself is implemented as C bar transpose y bar, alright. So equalizer is implemented as C bar transpose y bar, and for this we want to find the approximation error, that is how close is this to the vector 1 bar 2. Therefore, we want to find the approximation error. Remember, this is what we have started computing. The approximation error, which is equal to norm of H transpose C bar minus your vector 1 bar 2 whole square, and here we have substituted the expression for C bar. So this expression for C bar we substitute here, C bar is in fact equals H transpose inverse H into 1 bar 2 over here, and what that gives us is basically the approximation error equals, that is the error equals norm of H transpose transpose inverse H into 1 bar 2 minus 1 bar 2 whole square, and this matrix, that is H transpose inverse H, we call this matrix as your matrix PH. Remember, we said this is the projection matrix for the range for the for H transpose. This is the projection matrix for H transpose, and now we can write this as, this is equal to, what is this equal to? This is equal to, now denoting this by, so PH into this vector 1 bar 2 minus 1 bar 2 norm square, which is basically equal to norm of PH minus the identity matrix into the vector 1 bar 2 whole square, and which can be further simplified as basically norm V bar square is V bar transpose V bar. So this is PH minus identity times 1 bar 2 transpose into the vector itself, that is pH minus identity into 1 bar 2, which is basically 1 bar 2 vector transpose times pH minus identity transpose pH minus identity into this vector 1 bar 2. And at this point what we said is we want to explore the properties of this projection matrix pH, which is the projection matrix of H transpose. We wanted to explore the properties of this matrix pH. Okay. So, we want to explore properties of pH. Explore properties of pH, and we said that pH satisfies the following two properties. One, pH is symmetric, which means pH transpose equals pH, that is the transpose of pH equals itself. Two, more importantly, pH square, that is, this is a very interesting property, pH, the matrix multiplied by itself, pH times pH is indeed equal to pH. So, these are the two properties that this matrix pH satisfies, and we now employ these two properties. We want to now employ these two properties to simplify the expression for the approximation error, that is 1 bar 2 transpose into pH minus I transpose into pH minus I times 1 bar 2. So, we want to simplify this employing these properties, and that is what we are going to do now. So, employing these properties, I have this is equal to error is equal to. So, we already derived our error is equal to this is equal to basically we have 1 bar 2 transpose into pH minus I transpose into pH minus I into 1 bar 2, which is equal to 1 bar 2 transpose into pH transpose minus I transpose into pH minus I into 1 bar 2. Now, this is equal to now you can see pH transpose, this is equal to pH itself, because that is what we have proved earlier, and I transpose is the identity matrix itself. So, this is 1 bar 2 transpose into pH minus identity into pH minus identity into 1 bar 2, which is equal to, now you can see this is basically equal to 1 bar 2 transpose times, now multiplying out the quantities in the brackets pH into pH minus I times pH, which is PS, minus pH times the identity matrix, which is pH, plus identity times the identity, which is identity itself, times 1 bar 2. Now, you can see pH times pH is equal to pH itself. So, this is basically your 1 bar 2 transpose, where we are using the property that pH times pH is equal to pH. So, this is pH minus pH minus pH plus I times 1 bar 2. So, these two pH cancel, and what we have, this is equal to 1 bar 2 transpose I minus the matrix pH times 1 bar 2. So, we can in fact simplify this as 1 bar 2 transpose times I minus the matrix pH times 1 bar 2 transpose. This is the expression that we have developed for the approximation error so far. We can simplify it even further. In fact, we can now simplify this as the error is equal to 1 bar 2 transpose into identity into 1 bar 2, which is 1 bar 2 transpose 1 bar 2 minus 1 bar 2 transpose pH times 1 bar 2. Now, let us explore these quantities 1 bar 2 transpose 1 bar 2. Now, this quantity 1 bar 2 transpose 1 bar 2, this is the row vector 0 0 1 0 times the column vector 0 0 1 0, which is basically equal to 1. Now, this vector, this entry 1 bar 2 transpose pH 1 bar 2, this is basically 1 bar 2 or 1 bar 2 transpose pH into 1 bar 2. This is basically 0 0 1 0 row vector times pH times the column vector 0 0 1 0, and you can check that all this does is basically it picks the 2 comma 2 entry of the matrix pH. So, what this does is picks the, so this is pH 2 comma 2, what this denotes is this notation denotes 2 comma 2 entry of matrix 2 comma 2 entry of the matrix pH, where the counting is from 0, entries are counted from starting that is, this denotes the 2 comma 2 entry of the matrix pH, that is the entry in the second row and second column, but the counting has to start from 0, that is you start counting from 0th column, first column, second column, so on, 0th row, first row, second row, so on, and you look at the intersection of the entry at the second row and the second column where the entry is. And now, therefore, the error, the approximation error is given as is given as 1 minus, well, let us write it down completely, 1 bar 2 transpose 1 bar 2 minus 1 bar 2 transpose pH into 1 bar 2, which is equal to 1 minus pH 2 cross 2, that is the approximation error. So, let me write this down completely, the approximation error one minus pH 2 cross 2, this is the expression for the approximation error, where the matrix pH, let us mention that again, pH is the projection matrix of H transpose, which is H transpose H transpose inverse times H, where pH is the projection matrix pH is the projection matrix of H transpose, where pH is basically the projection matrix of H transpose, and the approximation error is 1 minus the 2 comma 2th entry, that is the entry in the second row and second column of the matrix pH, where the counting starts from 0. Okay. All right. So, that is the expression or succinct or the or a simplified expression for the approximation error, and denotes how well this equalizer is able to approximate that ideal desired vector 1 bar 2. Remember, that is what our initial goal was, to try to approximate H transpose C bar as close as possible, to make it as close as possible to this vector 1 bar 2, so that you remove the intersymbol interference from the symbol xk, that is intersymbol interference on the symbol xk arising from the symbols xk plus 2, xk plus 1 and xk minus 1. All right. So, to understand this better, let us do a simple example. So, to understand this better, let us do our previous example. So, the example for an approximation error so let us do this example for our approximation error. So, to understand this better, let us do an example and let us go back to the simple, that is the 2 tap ISI channel that we had considered previously. That is, remember, for our equalizer we had considered yk equals xk plus 0.5 xk minus 1 plus Vk. This is the ISI channel. So, we have L equal to 2 taps, L equal to 2 taps, H0 equal to 1 and H1 is equal to 0.5. So, we are going back. So, to look at a simple example for this approximation error, we are going back to our previous example where yk, with the intersymbol interference channel that we had considered, is yk equals xk plus 0.5 times xk minus 1 plus vk. Vk of course is the noise, and the channel taps, this is a 2 tap wireless channel, intersymbol interference wireless channel, where H0 equals 1 and H1 is equal to 0.5. So, this is the simple 2 tap ISI wireless channel example that we are considering. Okay. And for this, let us now derive, we have already derived the equalizer, let us now derive the approximation error for this. So, we have L equal to 2 for R equal to 3 for a 3 tap equalizer, for R equal to 3, that is our 3 tap, for R equals 3, that is our 3 tap equalizer. We have seen that H, the matrix H is basically 1, 0.5, 0, 0, 0, 1, 0.5, 0, 0, 0, 1, 0.5. Okay. So, this is the matrix. Now, we want to compute, now for this naturally remember the projection matrix of H transpose is a key to evaluate the approximation error. So, we want to compute the projection matrix of H, which is H transpose H transpose inverse times H. Okay. So, we want to compute the projection matrix of H transpose projection matrix of H transpose, which is given as PH equals H transpose H transpose inverse times H. Now, let us start by computing H transpose, although we have already done that before, let us do it again for the sake of completeness. H transpose, we have already written down the expression for H, that is your 3 cross 4 matrix, which is 1, 0.5, 0, 0, 0, 1, 0.5, 0, 0, 0, 1, 0.5. And H transpose is 1, 0.5, 0, 0, 0, 1, 0.5, 0, 0, 0, 1, 0.5. This is a 4 cross 3 matrix, and when I multiply these two matrices together, what I get is basically I get the matrix, the 3 cross 3 matrix, which is 1.25, 0.5, 0, 0.5, 1.25, comma 0.5, 0.5, 0, 0.5, 1.25, which now writing as fractions, we can write H transpose H, which is equal to 5 by 4, half, 0, half, 5 by 4, half, and the last row is 0, half, 5 by 4. So, this is basically your 3 cross 3 or basically your R cross R matrix H transpose R cross R matrix H transpose H. Now what we want to find next is basically we have to find H transpose, or we want to find HH transpose. I am sorry, this is HH transpose. So this is HH transpose, and now what we want to find is basically we want to find HH transpose inverse. Now to find that we have to basically start by finding what is the determinant of HH transpose, correct. So we have to find first the determinant of HH transpose. We have already found that. You can refer to the previous modules. This is the determinant of HH transpose. This is the determinant of HH transpose, which is 85 divided by 64. Now HH transpose inverse is equal to 1 over the determinant times the matrix of cofactors. Remember, we computed this also, that is 21 divided by 16 minus 5 by 8, 1 over 4 minus 5 over 8, 25 over 16 minus 5 over 8, 1 over 4 minus 5 over 8, and 21 by 16. Remember, this is your matrix of cofactors. This is the matrix of cofactors, and now taking the factor of 64 inside, what we have is H transpose H inverse is 1 over 85 times 84 minus 40, and you can check all of these calculations, minus 40, 100 minus 40, 16 minus 40 and 84, and this is basically the expression for HH transpose inverse, and this is something that we have already derived, that is for this frequency selective channel Y, Yk equals xk plus 0.5 xk minus 1 plus Vk we have derived. We formulated the system model to derive the expression for the matrix H, and from that we have derived HH transpose, and we have now computed HH transpose inverse also. Okay. So now we have to compute the projection matrix. Okay. So to compute the projection matrix, let us first start by computing HH transpose inverse times H. We have just computed HH transpose inverse, so that is basically your 84 minus 40 16 minus 40 100 minus 40 16 minus 40 84 times H times the matrix H, and remember the matrix H is 1, that is 1.5 0 0 0 1 0.5 0 0 1 1.5, and this is equal to, you can multiply that out, and now you can see this matrix is given as basically 3 cross 3 times 3 cross 4. So, that gives a 3 cross 4 matrix, that is 1 over 85 times 84, 2 minus 4, 8 minus 40, 80, 10 minus 20, 16 minus 32, 64, 42. This is the expression for your matrix H transpose inverse times H. Okay, so we have now computed the matrix H transpose inverse times H. Now I have to multiply on the left by the matrix H transpose to finally compute PH. So PH is equal to, and we will compute that also, PH is equal to H transpose times H transpose inverse into H, which is equal to, basically now H transpose is, we have seen this is the 4 cross 3 matrix 1.50, of course 0 1 0.50 0 0 1.5 times, I am going to bring the factor 1 over 85 outside, this is 84, the H transpose inverse H, I am substituting that, 84, 2 minus 4, 8 minus 40, 80, 10 minus 20, 16 minus 32, 64, 42, and of course there is this factor of 1 over 85, the factor which is brought out, and now when I simplify this, you get PH, finally multiplying this thing out, you get PH, the projection matrix of H transpose, that is PH, your matrix PH is equal to 1 over 85 times 84, 2 minus 4, 8, 2, 81, 8, minus 16, minus 4, 8, 69, 32, 8 minus 16, 32, 21, and this you can see, you can now, and now, so therefore this basically gives the your projection matrix of H transpose PH, which is basically H transpose H transpose inverse times H, and in this we have to take the 2 cross 2 element. So the 2 cross 2 element start counting from 0, the 2 cross 2 element, you can see this is given as basically 0, 1, 2, 3, this is the counting of the columns, the rows 0, 1, 2, 3. Now you can see the 2 cross 2 element basically corresponds to the second column and the second row, which is this element. So this is basically, of course there is a factor of 1 over 85 outside, so this is basically your 2 cross 2 element. Okay. And now using that, the approximation error equals 1 minus the 2 cross 2 element of the projection matrix H, that is 1 minus 69 divided by 85, 69 divided by 85, which is basically equal to 16 divided by 85. So the approximation error equals 16 divided by 85, and that is what we have, and this is the approximation error that we have been able to deliver for this simple example. So what we have done in today's module is basically we have started out with from where we left off in the previous module, and we looked at the expression for the approximation error for this least squares or the zero forcing equalizer. All right, we have simplified that using the properties of the projection matrix of H transpose, that is PH, which is equal to H transpose times H transpose inverse times H, and basically the approximation error we have simplified it as 1 minus PH of 2 comma 2, that is the 2 comma 2th element of this projection matrix PH, where the counting of the columns and rows is done starting from 0, and then we have done a simple example considering the ISI, the intersymbol interference channel Yk equals xk plus 0.5 xk minus 1 plus Vk, and we have, for this channel and corresponding to a 3-tap equalizer, we have computed this approximation error, and we have shown that this approximation error is basically given by this quantity, that is 16 divided by 85. Alright. So with this we will stop this module and we will explore other aspects in subsequent modules. Thank you very much.